class, we learned about electric potential and electric potential energy in the general terms. These are two quantities that are very important for analyzing the motion of a charge in an electric field. In this video, we're going to look more specifically at those two quantities when we have a point charge that's creating the electric field. These equations that we'll be learning in this video are we can only use them if we have a point charge as our source charge, or the thing creating the electric field. The two equations that we'll use in this case for the potential energy of a charge when we have a source charge that is a point charge is K Q1 Q2 over R, and the electric potential equation is K Q over R. Now these two equations might look pretty familiar to you because they look really similar to the electric force equation and the electric field equation, with two pretty important differences. The first difference you'll notice is that there are no absolute value signs around the Q's. That means that if we have a negative charge, go ahead and plug it in as a negative number. The other important difference is that R in this equation is not squared. So make sure that you don't accidentally square it since you're used to electric force and field equations. One other important difference that isn't obvious from these equations is that electric potential and electric potential energy is a scalar. That means if we're adding electric potential energies or electric potentials, we don't have to pay any attention to direction. We can just add those numbers together. One thing that makes these numbers a bit different than most other numbers that we've dealt with in physics is the fact that an electric potential of -5 is a lower potential than an electric potential of -2. So electric potential and electric potential energy follow the number line rules for numbers being higher or lower, or smaller or bigger, rather than the physics rules where we're used to thinking about the magnitudes of that number and the negative sign indicating direction. Let's look at using these equations in a problem. In this problem, we have a proton located at the point 6, -8 centimeters. We're asked to find the electric potential at the origin. Since it's a proton, we know that that's a point charge. So that means we can use the equation V equals KQ over R. Notice it is asking us to find the electric potential at a location. Remember, we learned in class that electric potential is a property of a location in space, as opposed to electric potential energy, which is a property of a charge. K is the same as it has always been, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Q, since it's a proton, is positive 1.602 times 10 to the -19th coulombs. And R, the distance that this this charge is located from the point where we're finding the electric potential, something that we need to calculate. We know the proton is located at 6, -8. So if I were to draw that, that would look something like this. So here's where my proton is located. So this R distance is the distance from the origin to the location of this proton. I know that I can use trig to be able to find that. Specifically, I'm using the Pythagorean theorem. And when I do the Pythagorean theorem, I find that that distance is 10 centimeters or 0.1 meters. When I plug these numbers into a calculator, I find that the electric potential at the origin due to this proton is 1.44 times 10 to the -8 volts. That's part A. Part B says that we've now placed an electron in the same scenario. It's at -3, -4. So here's where my electron is located. I'll label them so we remember which is which. Now we're asked for the total electric potential at the origin. Remember how I said how electric potentials are scalars? Just add them. So here's what I can do. I can calculate the electric potential due to that electron by doing AQ over R. And then I can just add this number that I get to the number that I got, answer that I got for part A to find my answer for part B. So 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. This time it's an electron, so we'll use negative 1.602 times 10 to the negative 19th coulombs. And for my distance, once again, something I need to calculate. Put that up in this blue up here. That one's also pretty easy to calculate using trig and Pythagorean theorem. And I get 5 centimeters or 0.05 meters there. When I calculate that value, I find that I get negative 2.88 times 10 to the negative 8th volts. So to find the overall potential at the origin, I'm going to add these two values for electric potential. The one that was my answer from part A and the one that I just calculated. When I add these two values together, I find that the total electric potential at the origin is negative 1.44 times 10 to the negative 8 volts. A lot simpler than what we dealt with electric fields, right? Part C is our last part left, and it says that with both charges in place, it wants to know the potential difference between the origin and the point negative 1, 0. Well, we already know the total electric potential at the origin. So to solve part C, you're going to need to find the electric potential at the point negative 1, 0 due to these two charges, and then you're finding the potential difference, so you're subtracting those values. Go ahead and calculate this and bring your answer and work with class to you when we meet.